Good afternoon. So this is lecture number 28, and yesterday we started discussion on the flow visualization. Today we will continue the same. So major idea of flow visualization is actually interface reconstruction, and after discussing the basic principles, then we will discuss one or two case studies where people have employed different optical probes for determination of the phase designs and phase reconstruction. Okay, so we were discussing about the principles, fundamental principles of different tomography techniques. So in this part we have next type of tomography is electrical conductance tomography. Okay, so in case of electrical conductance tomography, what we have, you can see these parallel wires. So these parallel wires are one set of wires which is called as array 1. Then we have second set of wires which are in vertical orientation, and these are designated over here as array 2. And then this is the third set of wires which are termed as array 3. Now you have to understand, because we are looking into the transverse plane, then these are appearing as a cross mesh of wires. But in actual practice, what we have array 1 at one transverse plane, then array 2 is at certain distance from array 1 in the axial direction. Is this point clear? So in between array 1 and array 2 there is some gap in the axial direction. Okay, then array 3, so again between array 2 and array 3 there is some axial gap, and that gap is actually very small, of the order of say 1 mm or so. Okay, so in this case what will be happening, this array 1 and array 2, between these two wires you may find that at some portions between the two wires there will be contact of liquid, in some portion there will be contact of gas. So for example, the corresponding thing you can see over here, say this is your one wire, this is your other wire. So here you can say that this is one liquid contact between these two wires of length L1. Then second liquid contact is of say length L2. So likewise we can have multiple lengths contact between the two wires, and depending upon the contact of liquid and the contact of length, we will be having corresponding different values of the conductance which we will be obtaining from this. Okay, so ultimately if you see the complete structure, the overall resistance of the complete structure will be nothing but summation of I varies from 1 to n 1 by Ri. Okay, so this is the resistance between the two wires. So between the two wires there can be contact of liquid at multiple points. Okay, so say if you have a bubbly flow situation, so say one bubble is here, other bubble is here, third bubble is here, fourth bubble is here. So if your wires are lying something like this, then what you have? You have somewhere this contact of liquid, then another contact of liquid, then another contact of liquid. So likewise you may have multiple contacts. Okay, so the total, so each contact portion will be having some corresponding value of the resistance. So that's why if you do sum of all these for a particular set, then you will be getting the total resistance. Okay, so typically what is done, the total resistance Ri of each section can be written in terms of RLO, where RLO is resistance of the total length if it is filled with complete one type of fluid. Okay, and now depending upon the intermediate length, we will be having actually ratio of Li by Lo. So using this data between the two wires, actually you can measure that how much fraction is covered with liquid and how much fraction is covered with gas. Okay, then similarly we will be doing this simultaneous signaling for all the consecutive set of wires. Okay, and using that information then you can utilize it for reconstruction of the interface. Okay, so this is the method of electrical conductance tomography. Then similar way you can have acoustic tomography. So in acoustic tomography, once again the fundamental principle is same, like we have to have some set of array different points, but despite electrical signal, now we will be having the acoustic signal. So for acoustic signal, what is done, say this is one transmitter of acoustic signal, and then this is connected through some guide wave guides. So these wave guides will allow the signal to particularly flow through this direction, and then we have in the cross direction other wave guides which are nothing but acting as the sensing wave guides, and then these are transferring the signal to the corresponding receiver. Now again the sound will be having actually different characteristics in liquid and gas, so depending upon that actually you can reconstruct the interface. So these are the basic principle. Now let's see how these principles can be actually employed for practical applications. Before that, let me also show you that whatever the measurements we were doing from these are nothing but instantaneous measurement, because I told you that though we have a continuous wire mesh structure distributed over the complete cross section, but whenever we are doing the measurement, our time of measurement is actually very fast, so that this is corresponding to one particular time. Okay, now because we are doing this for one particular time, if I just increase this time period, okay, so if I do the measurements and then I keep a record of measurement for some time interval capital T, and then if I take the averaging of the data at all the points for this entire time period T, corresponding to that actually I can get the value of time averaged phase distribution function or void fraction. So these are certain examples where, say if this is your cross section of the tube, so this is shown at certain angle, so at this cross section your phase density function is having variation something like this. So if phase density function is having variation something like this at different locations, this means this is nothing but the corresponding values of the void fraction. Okay, so here you can see, so this type of structure you have, so it means you have something like stratified flow situation, where one portion, in the top portion you have one type of fluid, and in the bottom portion you have other type of fluid, and you are getting corresponding values of the void fractions. So this is at different locations within the pipe, and particularly these are obtained for time averaged data at different locations. Okay, now let's see that how people have used this type of systems in the practical scenarios and some of the case studies. So one typical optical probe which is of non-intrusive type, it has been used recently somewhere in the years 2006 and 7, and this is used for identification of the flow regimes in different horizontal and vertical pipelines of gas, liquid and liquid flows. Okay, so if you see the configuration, so what they have this as pipe cross section, and in this pipe cross section at the top one source is placed, and at the bottom there is one detector, and then through some processing unit and data acquisition system some post processing of the data is done. Okay, so this is the actual photograph of the system. So in this actual photograph you can see this is a laser light source. Okay, so this laser light source is actually sending some light signal, then at the other side it is detector is detecting. Now depending upon what we have within the pipe, actually we will be having different signals available. So here you can see the total arrangement which is used for calibration. So in this case you have a tank, and in this tank you have, this is nothing but say stationary interface. So this interface can be in between gas and liquid, or this interface can be between two liquids. Okay, now in this tank this inlet is provided and this outlet is provided. So the function of this inlet and outlet is just to vary the interface height at different levels within the stationary tank. Okay, so basically the idea is to calibrate the system. And then corresponding to different heights, when the source is sending the laser light, it is detected at the detector level. Okay, so you can see the voltage, output voltage, which is detected by the detector is shown for, as function of non-dimensionalized water depth for air, water and air kerosene, kerosene water system. So what is the meaning of air water? Means bottom face is water, top is air, and the height from this point to this point is h, and total diameter of pipe is d. So h by d, for different values of h by d. So when h by d is 0, it means corresponding to that it is completely filled with air. And when h by d is increased and h by d is 1, then water level has increased, and corresponding to h by d equal to 1, it is now fully filled with the water. Okay, corresponding to this, you can see these are the values of voltage signals. So these voltage signals are actually shown with some arrow bar. Okay, so here you can see in an air water system, when light is coming, they have not observed any change in the signal for even different heights of the interface. Then this is the second case of kerosene and water. So here in place of air now the fluid used is kerosene. So for kerosene water system, when you have no water, pure kerosene is present. Corresponding to that, your output voltage is this one. And when you are increasing the thickness of water, so when you are increasing the thickness of water, basically you are allowing more transparent portion for the light to pass. Okay, so because kerosene will be having actually more absorption of the light, so because of that you are getting less signal. Because if your say sensor is a photodiode, so what is the meaning of photodiode? Depending upon the intensity of the light, it will be generating a voltage signal. Okay, so if say your more amount of light is absorbed, which was happening for the case of a kerosene, then you are having less signal, and once your water thickness is increasing, then your actually value of signal is actually decreasing. Okay, so this is the say calibration. Then again, because what has been done, now the sensor has been placed in, so this was the vertical orientation of the sensor when it is from top to down. Then again the sensor is placed in actually inclined orientation, and in case of inclined orientation, now it is your light ray will be passing something like this. Okay, so these are the corresponding output signals for this inclined orientation. Okay, now in case of inclined orientation, little bit you will be having actually decrease in sensitivity, because below this point it cannot sense, already your signal has actually reached this point. Now how this variation is taking place for the stationary interface, this can be actually further extended for a moving interface, and then how it can be utilized for actually detection of the different phases. So here you can see the first case. In this first case, in your pipeline you have smooth stratified flow. So smooth stratified flow means fluid 1 is at the top and fluid 2 is at the bottom portion. So once you have smooth stratified flow, there is not much curvature of the interface. So if there is no curvature of the interface, there will not be much reflection of the light wave. Okay, so that's why the corresponding output voltage is almost steady with time. So this is say tested for flow through a pipe for around 20 seconds. For almost around 20 seconds, there is no change in the signal. When you have this type of intermittent bubbly flow or dispersed flow regime, so in this case Small bubbles are actually flowing in a horizontal direction at the top pipe, and at the bottom section you have actually pure continuous fluid. So in this case what is happening, you have too much fluctuations in the signal. So now just by looking into raw signal you can say that this is for stratified flow and this is for dispersed flow. But if you further do some statistical analysis of this signal, then you can find more important quantifiable features based on which actually you can tell that for what type of flow what will be the associated statistical feature of the signal. Okay, so that is something which is shown over here. So here you can see that stratified versus stratified wavy flow is compared for flow of kerosene and water. So in these two cases, if you now look into the raw signal, it is very difficult to tell from the raw signal that your flow is stratified or stratified wavy, because this also you can assume almost as the constant signal. So that is something which depends upon one's visualization power. Okay, so that's why some significant outcomes should be there. So based on the statistical analysis, if you calculate the mean, standard deviation and kurtosis of this signal, and then if you calculate the occurrence of peak, so here you can see the peak frequency is occurring corresponding to a signal of around 0.9, and important point is this peak is having actually significant magnitude. Okay, and when you are actually having the stratified wavy signal, then your spectrum of the signal is more. So spectrum is increasing but its peak intensity is decreasing. So when spectrum is increasing and peak intensity is decreasing, corresponding to that the meaning is some irregularities are actually coming. This is the corresponding major intensity value of this particular signal. So corresponding to what level you have occurrence of maximum intensity. Yes. And then corresponding to the second case, you will be having now these small fluctuations also. So these small fluctuations, what will these do? These will now increase the spectrum of frequencies. So spectrum of frequencies will become wide and the peak intensity will actually decrease. Okay. You can do many things over here. So different people have done different things in the signal. So some people have used wavelet analysis, some people have used probability density function, some people have used fast Fourier transform. The major thing is you have to identify some key characteristics of the signal, and depending upon that key characteristics actually you can quantify the phase type. So similarly for different values of dispersed flow also it is done, and you can see when the intensity of the dispersed flow is increasing, then your peak intensity of the signal is actually decreasing and signal is becoming distributed for the wide range of voltages. Okay, so your peak intensity is increasing and then your fluctuations are actually coming in the signal output. And this is the comparison of the flow patterns which were determined from the optical system, and these flow patterns are then compared with the flow regime map of Angeli and Hewitt. So these boundaries are from the flow regimes of Angeli and Hewitt, and then based on the optical arrangement, if you have stratified wavy flow with droplets, 3-layer flow, then stratified mixed with oil, water and dispersed, then depending upon that what are the phases are occurring, these are shown over here, and in some areas you can see that there are some ambiguities in comparison to the flow regime map. So obviously near the border points there can be issues with the signal, and in other cases, because near the border points we say that whenever we have the transition boundaries cannot be specified by sharp lines. So typically transition boundaries have wide zones. Why? Because whenever you are having one particular flow pattern, and in that flow pattern if you are having the presence of the perturbation, then depending upon the stability conditions, your perturbations can either amplify or perturbations can die down. If perturbation is amplifying, then flow regime will be shifting from one to another. If perturbation is dying down, then it will be returning back to the original flow condition. Okay, so that's why it is, even in the physical scenarios also, even if we are not using the pure signal based measurements, then also it is very difficult to precisely specify the values of the transition boundaries. Okay, and in majority of the cases these transition boundaries also depends upon the physical description of the system. So physical description of the system means that if say some person has used inlet with some Y channel arrangement, some person has made Y channel in the vertical orientation, so there can be different possibilities in the system. Okay, so all these actually affects the particularly the flow regimes near the interface boundaries. Then similarly this is also compared for different systems with the data of Loic and Angeli as well. Okay, so this is the use of optical signals. So this optical probe is actually not very costly. This is a very cheaper system. So use of this low cost system is demonstrated over here for the phase detection. Now in this another arrangement, here the optical arrangement is actually shown. Again this is a low cost optical arrangement, and this is shown for reconstruction of the interface profile between the two phases. Okay, so in this case again what you have is you have a rectangular tank, and in this rectangular tank, this tank is made up of actually again the transparent material. So transparent material means you have access to light as well as you have access to the camera also you can actually use in order to determine the interface. So in this arrangement you have kerosene and you have water, and this central point is considered as the axis, and the different distances are actually measured from this central point. So you can see from the top how much thickness of the kerosene is there, that is actually depicted as Hx. Okay, and this is shown at some inclined orientation, so it means this is a generic case. It can be done for horizontal as well as for inclined orientation. And again here also you have one inlet and one outlet. Now in this tank what is done, in the top portion of the tank 10 photodiodes are used. So this is nothing but 10 photodiodes in a series, and there is some gap between these photodiodes. Say that gap is designated as pitch between the two photodiodes. Okay, now at the bottom one coherent light source is used. So this is a light source at the bottom, and typically this light source is having luminance flux of around 1500 luminous and 50 watts power. Okay, so power of this light source was 50 watt, and then the signal of these all photodiodes through data acquisition system is actually taken into a system. So this is the arrangement, that light source is at the bottom and photodiodes are at the top. Then you can see this is the actual photograph of the photodiodes, and these are nothing but silicon based PIN photodiodes, and their complete description is given. So these make is Hamamatsu, model is this, and photosensitive area. So typically when you use a photodiode, its construction may be larger in diameter, but it is having one central zone. You can see this central dark spotted zone. This is the zone which is actually sensitive to the light, and only this zone will be actually generating, will be helping in generating the corresponding voltage signal. So this photosensitive area of this particular model of the diode is 2.4 to 2.8 mm square. Okay, and then spectral response range of this type of diode is 320 to 1100 nanometers. So it means that if your input signal is having wavelength in the range of 320 to 1100 nanometer, then it will be giving you actually the output voltage signal. So typically it is covering the entire range of visible light. So any visible light source if you use, corresponding to that actually you can generate the signal out of this. Okay. And photosensitivity is 0.52 amperes per watt at wavelength of 780 nanometer. So it means that if there is one unit change in the wattage of the power, corresponding to that the change in current will be 0.52. Okay, and typically this is rated at wavelength of 780 nanometers, and if you move away from this, then actually you will be having less in generation of the current. Okay, and third important point is dark current of this is around 10 nanoamperes. So what do you mean by dark current of a photodiode? So dark current of a photodiode is if it is placed in a dark room and you are not giving any light to that, corresponding to that whatever current output it is giving, that is called as dark current or saturation current. Okay, dark current or saturation current of a photodiode. Now when this arrangement of photodiode is used, this arrangement of photodiode can be used in different modes. This can be used in photoconductive mode, this can be used in photovoltaic mode. So typically this photodiode in this particular experimental measurement is used in the photovoltaic mode. So photovoltaic mode is the one which is used in solar cells. Okay, so solar cells, what they do, corresponding to intensity they generate some voltage. So that is called as photovoltaic mode. Okay. And if you have say I as the current output which is coming from a photodiode, if you are giving some light to this, okay, so this I will be actually constituting of two things. One is saturation current and second is yes, photocurrent. So that is called as photocurrent. So I will be nothing but saturation current or dark current plus photocurrent. Okay. So now what is done in this particular experiment? First your uh, ratio of this height is maintained at different levels. So here you can see when your height was low, okay, initially say your entire section is filled with actually water. So when entire section is filled with water, corresponding to that value of current which you were receiving, that was IW. Okay. Now this IW, this has been used to non-dimensionalize the current output. So non-dimensionalized current output is IW minus I. I is corresponding to mixture of oil and water. And further it is non-dimensionalized with reference current of water. Okay. So this value of phi is plotted as function of time, and while this value is plotted as function of time, values of this h by x are maintained at different levels. Okay, so initially this is maintained at say h by d of 0.1. So whatever your entire container is, only 10% of the container is filled with kerosene and rest portion is actually filled with the water. Okay, and then at the same value you have allowed the signal to actually, you have continuously acquired the signal. After that, the depth of kerosene is increased from h by d equal to 0.1 to 0.2, And how it is increased? So in the previous arrangement you can see you can open this outlet. So outlet will be allowing the water to go down, and from the top you can fill in the more amount of kerosene from the top. Okay, so if you do so, then during this traveling period also you can see the value of signal has jumped from one point to other point. Okay, so this confirms that in this particular photodiode system you can make stationary measurement as well as the moving interface measurement. Okay, because when you are jumping from one step to other step, corresponding to that you are finding that there is the continuous change of the signal, and that change of signal is actually precisely obtained. Okay, so this type of jumping is done for different points till h by d is reaching to 1. Okay, and here you can see when you have h by d of 1, then this is your output, and when h by d is this, then this is your output. And in between these two jumps also you have actually continuous variation. So it means the sensitivity of the system is sufficient enough to mark the measurable change between this system. Is this one clear? So that is clear from this particular curve.
जैसे जैसे हम पानी कम करते जा रहे हैं वैसे वैसे हमारे पास करंट बढ़ रहा है
Yes,
तो
because here we have done IW minus I.
हाँ तो जब पानी होगा तो सबसे ज़्यादा करंट होगा पर जो अभी आपने बताया उसमें पानी कम हो रहा है तो करंट बढ़
No, what you can do here, this is IW.
तो इसके यहाँ पे सबसे ज़्यादा करंट होगा IW is maximum.
Yes, yes. So what you have done, you have non-dimensionalized the numerator as IW minus I. So when you are doing this minus I, you can see for water the value of this non-dimensional signal is becoming 0. Okay, so non-dimensionalization is in such a way so that it is reversing the trend actually. Okay, so this I is increasing, but non-dimensionalization is done IW minus I. So that's why that is reverse effect is actually visible over here. Okay. Now, another important observation is here you can see in the initial portion the jump between 2 points is more, and here the jump between 2 points is less. So it means once you have more depth of the kerosene, then change in signal between two levels is actually decreasing. So this is nothing but in this portion, particularly in this portion, you will be having less sensitivity of the system. Okay, and here you have high sensitivity. But this trend is actually consistent with one of the fundamental law which is called as Beer-Lambert's principle. As per Beer-Lambert's principle, if you have some light which is penetrating through certain medium, then depending upon the absorption strength of that material, so each material is having some absorption coefficient for a particular wavelength. If your thickness is increasing, then along with increase in the thickness, your change in signal intensity will be in exponential fashion. Okay, so that is something which is a universal law and characteristics of the material. So that is something which is evident over here. So these are the steady signals for each height, you can see, and the average of all these steady signals when it is plotted for different trials and then plotted with error bar, then you can see in between phase fraction h by b and the output signal phi, you can actually fit one exponential relations. Okay, so this is our now the standard master curve. Now by knowing the value of phi for any unknown distribution of phases within the system, you can actually predict the value of phase fraction h by b for the system. Is this point clear? So now what is done? Of course, when calibration was done, at that time the container was in horizontal orientation. Now the angle of the tank is actually varied for different orientation to see how accurately it actually predicts for inclined interfaces. So once you have oriented the interface at different angles, so first angle of inclination is 10.6 degrees. So if you incline your entire system at an angle of 10 degrees, because of the gravitational pull, interface will be remaining stationary. If you take photograph with reference to the inclined orientation, that will be appearing straight, and here you will be having actually inclined interface. And this is the photograph, and these points are nothing but the discrete data at sensor locations which are predicted by the sensors, and this trend line is actually fitted line in between all the points. So from this you can see that it is very closely predicting for different data, and here you can see if you simply calculate the slope of this trend line and the angle which you have specified actually in the tank. So if you plot this data, so specified angle versus obtained angle from the sensor, these are actually matching quite well. Okay. So it means if you have inclined interfaces, so there this type of measurement is actually working well. Then further, what was done, by doing some arrangement, this interface was subjected to oscillations. Okay, and then it is seen that whether the in the previous measurement this is a steady interface, but now you have a dynamic interface which is actually oscillating something like this. So when your interface is oscillating, corresponding to that, all these red colored points, scatter points, are from the uh, sorry, this blue colored line is actually measured data using image analysis. So when this interface was oscillating, corresponding to that you have done high speed photography from the front face, and with that high speed photography actually the location of the interface is predicted, and the location of the interface is actually shown with this blue colored line. And after that the data is also predicted from the sensors, because simultaneously sensors were also in the operation, and the data predicted from the sensors is actually shown over here. So you can see majority of the oscillating patterns and oscillation frequencies are actually captured well. However, if there are certain sharp peaks, these sharp peaks in some places actually there is some difference between the sensor data and the visualization from visualization data using the high speed camera. Okay, but majority of the overall trends are actually captured very successfully. And again you can see when your oscillations are large, there your variation is actually, or data is captured accurately, but once you enter in the low oscillation zone, then though these circles are a bit large in size, but here you can see that because of decrease in sensitivity you may experience slight differences in the two measurements. Okay. So this is for a particular sensor location. Now what you can do, because you have array of sensors, so in array of sensors what you can do, you can record the data for different sensors. So if you have say oscillation about some particular point, if you take the data of sensor one point above the point of symmetry and one sensor on the downstream of the point of symmetry, almost at the same locations, then you will be experiencing that both should give you the same value of the amplitude, but there should be difference in their phase difference should be there. So when say one interface is oscillating like this, so when this point is above, other should be below. So that is something which you can see over here. So when you have peak of one, corresponding to that in the other signal you have a valley. Okay, and these peak and valley have the phase difference. Is this point clear? Then third type of prediction is curved interface. Okay, so for measurement of curved interface, what is done? Entire experimental system was placed on a rotating platform. So this is some platform, and this platform is actually connected to a motor. This motor is connected to a variable frequency drive. So variable frequency drive, you can actually vary the RPM of the motor, okay, for same voltage and same value of frequency. Sorry, for same value of voltage and input current, okay. And then in this because your entire sensor arrangement is actually on the top of the platform, so you have to make some arrangement so that on, if everything is on this, then all your data acquisition system sensors, these requires actually power, okay. So as these requires power, you have to transform power to this system. So if you use extension wires, wired connections, then what will be happening? Yes, wrapping and unwrapping of the wire, okay. So because of this type of slip ring assembly arrangement is used, okay. So slip ring assembly arrangement means on a shaft one rotating ring is placed which has two terminals like this, and these two terminals are getting power from a contacting strip, which is, so these are the contact brushes, okay. So these contact brushes are stationary, these are giving power to uh, these two terminals, and these two terminals are then internally connected to this platform, which can actually simply transfer the entire which can transfer the electricity on this rotating platform, okay. So using this arrangement, then the entire system was rotated for different RPMs, and then you can see this is the curved interface profile actually, which is obtained uh, from optical signal. So it means if you have a curved interface, then also with sufficient accuracy actually your system was working. And third type is you have some interfacial waves. So you can see here, when you have a wavy interface, then for wavy interface also the system was able to predict well, but in certain portions, so here you can see there are significant differences, and these differences can come because of the, these significant difference can come because of the three-dimensional nature of the wave, okay. So sensitivity will be low when your system is majorly filled with the kerosene. So if you have too much, interface is too much close to the bottom part, then you will be having actually errors because of the sensitivity. But when interface is at the bottom, then the previous configurations where you have simply a straight oscillating interface, there the nature of the interface is almost planar. And when you have interface, whole platform is moving at a particular speed, then also your interface profile is steady. But when you have random wavy structure, so say number of waves are actually passing, reflecting the tank wall and then coming back, so there what you will be finding, you will be finding that your shape of the interface will not be purely two-dimensional or purely planar. So shape of interface will be three-dimensional. So because of the three-dimensional effects, when you are visualizing from camera, you may not get the actual profile at that point, okay. So there can be, because of the curve, some small adherence of the bubble or other parameters, which will be actually leading to, errors in measurement, okay. So it means that if you have to employ this type of system, then majorly it will be available for stratified flow regimes, and in case of stratified flow regimes also, the good accuracy will be achieved when you have planar interface, okay. If the nature of the interface is becoming three-dimensional, then because of the curvature effect in the third direction, you may have some sources of error, okay. So that is something there, what you need to do, you need to actually control the RPM, okay. So if you do rotation at very controlled RPM, then what will be happening? There will be phase stratification depending upon the density in an paraboloid manner. But if you start rotating at very high speed, then what will be happening? There will be intermingling between the phases and then bubbles will. Yes. Okay. So this is the like what I want to say, that a very simple system, say which is made up of 20,000 or 30,000, that can also be used for phase reconstruction, so reconstruction of the interface. But the thing is, you have actually very limited number of applications where you can employ this type of systems. Okay, and one quick application of this system can be for the flow rate sensitivity. So in terms of flow rate sensitivity, because we have seen that in the very previous curve, when we were jumping from one step to other step, then during that time when interface was moving up and down, corresponding to that actually we were able to see or trace the continuous variation of the interface. So that continuous variation of the interface in a known diameter system or in a constant cross section tank, it can be utilized for measurement of the fluctuations in the flow rates. How? Say you have a tank over here and fluids are actually coming in stratified manner. If flow rate of this fluid is increased and flow rate of bottom fluid is actually decreased, this is increased, what will happen? This interface will start moving towards the bottom direction. If flow rate of this one is increased and this is decreased, then interface will start moving towards the top direction. So if you have some process parameter in the industry where you want to actually control the flow rates of the two systems, then depending upon the interface location, you can see whether your flow rates are decreasing or increasing for a particular phase, and if you want to control, you can utilize this information to control the flow rate as well. Okay, but only thing is that if you have to employ this type of system, you need optical access. Optical access means your system should be transparent. Okay, so this is the application for variable flow rate. So here you can see when the flow was maintained at one particular flow rate, then suddenly the flow rate was changed to some second flow rate. So that type of changes in the flow rate also this system was actually able to predict with sufficient accuracy. Okay, so the basic idea is, why I am showing this, the basic idea is you should know the fundamental principles. Okay, you should know the fundamental principle and fundamental or basic layout of the system, that how this work. Then once you know these two things, after that if you have to employ this system for any practical applications, what you need to do, you need to design the systems by your own. Okay, so majority of the experimental systems, even for single phase systems also, when you do experiments or when you do say utilize some measurement techniques for industrial systems, instrument and sensor comes ready made. Okay, so that is depending upon your requirements, you can select the instrument depending upon required accuracy, required range of measurement, okay, and your application. But how to integrate that sensor or that measurement device to your system, that is something which you have to actually design. Okay, even if you have to simply measure the flow through a pipe, flow rate if you want to determine in a pipe, so what you need to do, when you place even a single venturi meter or orifice meter, you have to develop the system by your own. And for different applications, even your venturi meter and orifice meter also has different designs and different design considerations. So the basic idea is, when you do the experiments or when you do the measurements, you should know the fundamental principles, you should know the basic layout of the system. After that, depending upon your requirements, actually you have to design the system, you have to integrate the system to do some particular measurement. Okay, now after this quickly we will talk about flow velocity measurement in the next lecture, and then we will switch to computational methods. Okay.